Hello, welcome to my talk. Delighted to be here and talking to you all today. I'm going to be talking about computer vision for social presence in mixed reality, and I will explain what that means as we go. We humans are a very social, collaborative species. In normal times, we would spend huge portions of our working hours together in communication, in collaboration, with our friends, families, and co-workers. It's interesting to look at the history of human communication. Of course, things started very much with in a low-tech setting where we could only talk face-to-face. Culture evolved and new forms of art allowed us to communicate both across time and across space more easily. The written word, again, further expanded those horizons. And since then, there's been a huge number of technological innovations, many of which are still in active, very active use today. It's been fascinating to see how these technologies have powered us through the pandemic, with hundreds of millions of people around the world forced to work from home. It's been incredible to see that the video conferencing technologies that we have today can actually enable that style of working at a scale that we've never experienced before. And yet, I think all of us would agree that there is a huge downside to this, and we've all experienced the fatigue that comes from staring for hours at an end at a flat screen with a grid of people staring right back at us. It's not a very human experience. I believe we're on the cusp of a new form of technology for enabling communication. And I think this is because there's a confluence of advances in three technology fields: mixed reality devices, such as the HoloLens or VR devices, that allow us to render a virtual hologram in 3D in front of you in your room, as if a person's really there. Advances in AI are allowing two things, both, first of all, to track the user, to understand their motion, their appearance at a level of detail that we've so far not been able to achieve, but also then at a remote location to photorealistically render a representation in 3D of you as an individual that goes beyond the uncanny valley. And finally, the cloud. Now, while the cloud will of course be a major part of any communication story, in this particular instance, it has the potential to offload some of that heavy AI compute off our mixed reality devices, which we know are going to be constrained from a compute perspective, especially as those devices start to shrink down on our heads. And so I believe that the confluence of these three trends and advances in these three areas is going to finally enable what we call social presence in mixed reality. And this is going to be a journey that's going to take a bit of time, but it's also a journey that we have started on already. And just a couple of weeks ago, we announced Microsoft Mesh. And I'm going to play this quick video to introduce Mesh to you.
We have two planes right now on the same trajectory.
As we put people first, technology fades into the background and feels like anything but.
Aisha, what do you think?
I think if we had 330, maintaining 2800, we'll be clear for approach.
Excellent.
This changes the way we see the world, and in turn, changes the world we see.
These numbers are looking great, actually.
There's promise in the possibilities, and what we see and create next will stretch the imagination.
Good morning, Sarah.
Morning.
Slowly coming towards the thumb.
A world without boundaries.
Good job. A lot better than yesterday.
Yeah.
Excellent. Slowly bring the
A
arm
world
down.
where technology enhances, not limits, humanity. With people front, center, and in the spotlight. The future is here. And here can be anywhere. Introducing Microsoft Mesh.
So I hope that gives you a little bit of an idea about what Microsoft Mesh is and the kinds of technologies that we're talking about with social presence. It really is all about enabling people to come together, even though they're remote, and share a 3D experience and feel like they're there, and you feel like the remote people are with you through technologies such as avatars and holoportation. Now, there's all sorts of benefits. If this really does pan out in the way that we're expecting over the next 5 or 10 years, this could really revolutionize how we communicate across the planet and bring all sorts of benefits, and moreover, all sorts of savings in carbon emissions from travel, time and money. In general, if you can send bits rather than atoms across the world, it's much better for everyone. Now, looking at a high level at what we're trying to achieve, on the left, you're seeing a variety of different input scenarios, and we want to be able to support as many of these as we can, whether that is just sensors on your head, and sensors on your head that can track aspects of your motion, your expressions, through a HoloLens or a VR device, or whether that's sensors and devices that you stick in the room, like your phone, or indeed a studio where you might capture yourself with more fidelity. And we're going to have to sense and understand something about the user, transmit that over the wire, and at the other end, recreate your likeness. And this will come in a variety of options, right? Of course, I think the holy grail is we want to get to true photorealism that crosses far beyond the uncanny valley and really does look like you. And that's on the cards, and that's coming. But even when we can do that, people will sometimes choose for some scenarios, especially for entertainment ones and social ones, where they might represent themselves in other ways, such as characters from movies or cartoon avatars. And in between, and again, this is a very, very high level picture, but in between, there's essentially two main components. One is human understanding AI that takes the data from those sensors and infers as much as we can about your facial expressions, your body pose, and your appearance. And sometimes we'll rely on prior information or offline enrollment to help this. But given that, we can transmit that data across the wire to the other end through the cloud, and render you in the form, in the likeness that you are, and the representation that you choose. To give you an example of one of the early projects we did in this space, this is now about a year old, this video, a project called Human Motion Models, where we started to look at what you could do with just the relatively impoverished sensors we have on a HoloLens 2. And so this video shows that from just the head tracking and hand tracking cameras that we have on HoloLens 2 on the left, we can infer a really pretty reliable and lifelike avatar of you and the motion that you're performing here on the right. So this is a sort of great example at the low end when you've got very impoverished sensors and you want to do something pretty fantastic. Now, with any kind of technology that has potential huge ramifications for how people communicate and how society operates, ethics is a huge part of the equation and a very, very important part of our work. And I'm very glad that we've got Microsoft's AI principles, as we see here, to guide us on this journey, because this is particularly relevant for social presence. Just looking at two of these for a second, privacy and security. If we're able to really represent you remotely, well, you better have trust in us that we are going to do that. We're going to maintain your privacy. We're going to keep that information secure, so that nobody is going to sort of take over your likeness and use it for nefarious purposes. That's absolutely critical. And another one, inclusiveness. We're building this technology to represent humans, and humans come in all sorts of shapes, sizes, ages, genders, races, and we need to be able to represent all of humanity without bias in this technology if we're really going to empower everyone on the planet with what we're working on. Now, that leads nicely on to the next short section on synthetic training data. One of the things that this is a subject that's close to my heart, I've been passionate about for over a decade now. And people ask, why would we want to use synthetic training data to train our AI algorithms? Why not use just real data and manual labels? Well, beyond the sort of simple answer about the expense of labeling things, I think the two main reasons to explore this, and the ones that excite me, one is exactly to deal with that, to deal with that inclusivity and be able to control the variation in the data to reduce bias and increase diversity. Furthermore, you can get really high quality labels. There's no annotation noise or error in these that manual annotation would bring. And in fact, as we'll see in a moment, you can generate labels that are basically impossible to annotate by hand. Now, of course, any kind of synthetic training data also needs to have high realism, because if it doesn't have sufficient realism, it's not going to generalize when you train on synthetic and test on real data. There's been a variety of exciting work in this space over many years, and and I'm excited that actually over the last year or two, there's been an acceleration in the adoption of this this technology, and I'm very excited to see what the future holds here. We've been working on this in the Mixed Reality and AI labs, and developed a synthetic face data pipeline, as we can sort of see illustrated here. Now, at its heart, this is fairly reasonably standard stuff. You take a parametric face model, you add a density expression, you then render that with texture, you add some hair models, clothing, environments. But we've gone to quite some efforts to make sure that this really does represent the whole of humanity, and gone the extra mile to add that diversity into our data generation pipeline. So just a few examples. Here's just a few examples of heads with hair. Now, looking at these, and just to be clear, this is not something we would use to represent you to a human. This is not an avatar. This is something that we all use to train our data. So even though these look a little uncanny, some of them at least, that doesn't really matter, as long as when we train our algorithms, it generalizes. AI algorithms, it turns out, don't seem to care about the uncanny valley in the way that humans do. And of course, we can generate sort of all sorts of variations. So here's some lighting variations. We can add accessories, hats, glasses, face masks, headsets, different clothing. And this starts to give you the diversity that you need to take this kind of technology in the wild and generalize to in the wild real images. And so with this pipeline, we can essentially generate unlimited training data with incredibly high diversity. And we're seeing that this kind of technology is now enabling us to match the state of the art on real benchmark data sets. And so here's a few examples from one of these data sets on a semantic segmentation task. And these results have seen no real training images, only the synthetic data I just showed you. And we can match the quality of data sets which have had to be manually labeled. But perhaps more importantly, we can go much further. And so with a pipeline like this, we can generate kind of arbitrary different forms of ground truth. We could generate albedos, normals, depth maps, masks, UVs, and the vertices of the mesh. And that, if you get this kind of data, which is incredibly hard to get through manual annotation. There's some interesting papers on using GANs to generalize from a few manual examples, but even that, I think, would struggle to get quite the variation that we're seeing here. But with this, you can start to do all sorts of interesting tasks that you wouldn't imagine were reasonable to do. So here's a fairly standard machine learning algorithm applied on dense landmarks trained purely on synthetic data. And we can generalize just straight out of the box onto real imagery, even predicting things like the ears, admittedly with a little bit of noise, but we can predict occluded things quite well. Here's another little experiment we did where you can actually predict depth from RGB. Now, I'm not trying to claim that the results here are state of the art, but you know, we literally did this experiment in 24 hours, which would have taken, you know, weeks, if not months, if we had had to rely on real data to collect all of that, label that, and then train. The other nice thing about our pipeline is, because partly we use it to develop algorithms for our HoloLens devices, is that you can zoom up really close. And so on the left, you can see some synthetic training images of eyes. And on the right, you can see a model trained on these images and tested on real data from a real HoloLens eye tracking camera and generalizing beautifully. So that's all I wanted to say today about synthetic training data. As I say, very exciting. I'm very excited by the possibilities here and the technologies in the social presence space that this is enabling. Moving on then to one more quick topic, neural rendering. And this is something I'm very excited about because I think it's probably the way that we cross over the uncanny valley in terms of representing your likeness in a remote location. Neural rendering is a space that has exploded into the community over the last few years, from sort of low-res, grainy face images in the first GAN work, all the way to high-resolution, photorealistic images of people, excuse me, of people, objects, and scenes in the last year or two. We did some work on this space at ECCD last year. This is a paper called Config. And here we actually used the synthetic training pipeline I showed you a moment ago to shape the latent space of the network such that we had control over it. We could control lighting, we could control pose, expression, even things like facial hair. Here's a few more examples of that where we can, you know, again, we've got control over all of these different kind of parameters that you might want when you're animating these things. And this was great, but it was still very much in the 2D domain. And you could imagine rendering a stereo pair using this kind of technology. But when we, you know, what really excited me and many people in the community last year was the neural radiance fields paper from Mildenhall et al., which showed how you could use neural networks to encode detailed and beautiful scenes, 3D scenes, and then render novel views with previously unseen quality. We've been exploring ideas in this space, and here's some examples of Nerf-like technology applied to faces, where you could now go and get yourself scanned offline and then reanimate your face online at really fantastic quality. And, you know, it's not completely artifact free, but it looks very natural. And I think, you know, for most people looking at themselves when they see this, it feels like it really is you. One of the problems with Nerf has been its computational demands. And so just a quick plug for Stefan and Marek's talk later on, where they will show you how you can speed up Nerf by about 3,000 times by factorizing some of the approach. And this is really starting to now open up the real-time applications of neural rendering that we're going to need for social presence applications. So that's all I wanted to say there. I'll wrap up back on this slide. I am incredibly excited about the possibilities for social presence in mixed reality. We have a long journey ahead before it really has earned its place on this slide. But I hope and expect that over the next 5 or 10 years, this will become mainstream and finally allow people to communicate remotely with approaching as good as being there face to face. So with that, I'll say thank you for your attention. Thanks for joining the event. And I think there's some time for some questions.
Thank you very much, Jamie. So we have a question from Priya Aswani, who asks, can you share a bit more about the use of synthetic data to correct for class imbalance, etc.?
Yeah, so the idea here is that as long as your training set for, because we have training sets for the synthetic data itself, we collect scans from diverse populations across the world to generate the parametric models that we use then to generate more training data. As long as we're very careful at that, we can ensure that the data and in the textures that we use, the hairstyles that we use, we can pretty much ensure a very uniform distribution across the world's population when we sample that. And in fact, I didn't show results here, but we've done experiments where you can actually quantify how much you can reduce bias across, for example, different skin tones.
Thank you very much, Jamie. So I have no further questions at this stage. So I would thank you again for your talk. And then hand over to Marek Kowalski for the next session.